Imagine you have a single clean photograph, a cat, sitting in a patch of sunlight. Now imagine slowly, gently sprinkling static onto it, a little at a time, until nothing remains but pure random noise. Today we're going to understand how a machine learns to run that process backwards, conjuring a brand new image out of pure chaos. This idea powers the image generators you've heard about, but underneath the magic is a surprisingly simple pair of moves. Destroy information in tiny steps, then learn to undo one tiny step at a time. Everything else is bookkeeping. Let's start with the destruction, because it's the easy half. We take our clean image and add a small amount of Gaussian noise. Gaussian just means the noise values follow the familiar bell curve, mostly small nudges, occasionally larger ones. One dusting of noise barely changes anything. The cat is still obviously a cat, but we don't stop at one step. We repeat this again and again, each time adding a little more noise on top of what's already there. Watch what happens across many steps. The edges soften, the colors bleed into speckle. Somewhere in the middle, the cat becomes a ghost, and by the end, the image is indistinguishable from television snow. This whole sequence is called the forward diffusion process. Diffusion, like a drop of ink spreading through water until the color is uniform everywhere. Information spreads out and dissolves until it's gone. Here's the crucial thing about the forward process. It's completely mechanical. There's no learning, no cleverness. We chose the noise ourselves. That means at every single step, we know exactly how much noise we added. But how much noise should each step add? Too much and the image dies too fast. Too little and we'd need thousands of steps. This choice is governed by something called the noise schedule, and it's worth looking at carefully. Let's graph it. On the horizontal axis, the step number from the clean image at 0 all the way to pure static at the end. On the vertical axis, how much of the signal survives versus how much is noise. We'll plot a curve that starts high, meaning the signal is fully intact, and slides down to 0, meaning the signal is completely gone. A common choice makes this a smooth, gentle S-shaped descent rather than a straight line. The shape matters. Near the beginning we add noise slowly, preserving delicate details as long as possible. Near the end we can afford to add it faster, because there's little left to protect. This careful pacing is what makes the whole thing learnable. There's a beautiful mathematical bonus hiding here. Because each step adds independent Gaussian noise, we can actually jump straight to any noise level in one shot. We don't have to simulate every intermediate step to get there. Concretely, a noisy image at any step is just a shrunk-down version of the original plus a scaled dollop of pure noise. The schedule tells us exactly how much to shrink the original and how much noise to mix in. This one-shot property is a gift for training, and we'll cash it in shortly. But first, let's confront the real challenge. We know how to destroy an image. Can we possibly learn to reverse it? At first this sounds impossible. If I hand you a frame of pure static, there are countless clean images it could have come from. The information really is gone. So how could any procedure recover it? Here's the key insight. We don't try to leap all the way back in one impossible bound. We only ask a much humbler question. Given this slightly noisy image, what did it look like just one step less noisy? Undoing one tiny step is a far gentler request. The two frames are almost identical. The difference between them is just a small specific patch of noise. And predicting that small patch of noise turns out to be something a neural network can learn to do remarkably well. So let's reframe the entire problem. Instead of a network that paints images, we build a network that answers one question over and over. How much noise is in this picture, and where is it? Notice how clever this is. We turned a mysterious creative act, generate a beautiful image, into a concrete prediction task, estimate the noise. Prediction tasks are exactly what neural networks are built for. And now the one-shot property from earlier pays off. To make training data, we take any clean image, pick a random step on the schedule, and jump straight to that noise level. Critically, we generated the noise ourselves, so we know the exact answer. We feed the noisy image to the network and ask it to guess the noise. Then we compare its guess to the noise we actually added. The gap between them is the error we want to shrink. We nudge the network's internal dials to make that error a little smaller. Then we do it again with a different image, a different step, a different noise sample, millions of times. One subtle but important detail: we also tell the network which step it's looking at. Noise at step 5 looks different from noise at step 40. Knowing the step is like knowing how deep underwater you are before you start swimming up. After enough training, the network becomes an expert noise spotter. Hand it any image at any noise level, tell it the step, and it can point to the static that shouldn't be there. Now comes the fun part, using it to generate. We begin with a frame of completely random static, not derived from any real image, just fresh noise we sampled ourselves. This is our blank canvas, except the canvas is pure chaos. We tell the network this is the very last noisiest step, and we ask our question, where's the noise? It hands back a prediction, a full map of the static it believes is present. Now the pivotal move. We subtract a small portion of that predicted noise from our image, not all of it, just a careful step's worth, exactly matching the amount the schedule says was added at this stage. After one subtraction, the frame still looks like static to our eyes, but mathematically it has taken a single step back up the ladder, from the noisiest level toward something very slightly more structured. We add a tiny bit of fresh randomness back in, which sounds counterproductive, but it keeps the process from collapsing and lets it explore. Then we repeat. Predict the noise, subtract a step's worth, nudge back one level. Let's run this loop and just watch. Over the first several iterations, the pure static begins to develop faint, coarse blobs of color. No shapes yet, just regions that are no longer perfectly random. As the steps continue, those blobs sharpen into rough forms. A dark mass here, a lighter field there. The network keeps answering the same simple question, and structure keeps precipitating out of the noise. Around the midpoint of our 50-frame journey, you can start to guess what the image wants to become. The overall composition locks in first, where the subject sits, where the background falls. Then, over the final stretch of steps, the fine details arrive. Edges crisp up, textures appear. What was a fuzzy suggestion becomes whiskers, fur, a glint in an eye. The last steps are all about polish, and there it is. From a frame of meaningless static, after 50 patient steps of predict and subtract, a coherent image has emerged, an image the network was never explicitly shown, assembled entirely from its learned sense of what noise looks like. Let's pause and ask the deeper question. Why on earth does subtracting predicted noise over and over produce something meaningful? What is really happening in each of those little steps? Picture the space of all possible images as a vast landscape. Almost every point in it is garbage, random static. Real, meaningful images live on a thin, winding surface within that space. We call it the data manifold. Adding noise to a real image is just pushing a point off that thin surface, out into the surrounding wasteland of randomness. The more noise, the farther out you drift. So reversing noise means finding your way back to that surface. And here's the punchline. Predicting the noise is secretly the same as pointing toward the manifold. The noise vector and the direction home are two faces of the same arrow. This is why people describe each step as a gradient nudge. A gradient is just the direction of steepest improvement, and here, improvement means becoming more like a real image. Every subtraction takes one small step downhill toward the valley where real images live. Now you see why we take many small steps instead of one giant leap. Far from the manifold, the network's sense of direction is rough, only approximately right. A small step keeps us from overshooting into a new patch of nonsense. As we get closer, the network's guidance grows more reliable, and the curving path steadily homes in. 50 gentle nudges trace a smooth route from the wasteland of static all the way onto the surface of believable images. And because we started from random static and injected little bits of randomness along the way, we don't land at the same spot every time. Different starting noise curves toward a different real image. That's where the endless variety of generated images comes from. Let's tie the two halves together one last time. Forward. Take real images and dissolve them into noise along a fixed schedule. No learning required. That gives us endless practice pairs of noisy image and known noise. Reverse. Train a single network to spot the noise, then start from static and subtract predicted noise step by step, each subtraction a small gradient nudge toward the data manifold, until an image appears. That's the whole engine. Two processes, one fixed and one learned, meeting in the middle at a humble question asked over and over: where is the noise? Answer it well enough, and you can turn chaos into anything. The images you've seen generated by these models aren't retrieved from a library or stitched from pieces. They're grown step by step from noise, along a path the network learned by studying how images fall apart. Understanding that path is understanding diffusion. If this made it click, subscribe for more visual math.